not a bad idea to go ahead and see if you can work this problem through on your own, um, and then come back and see if you got the same answers. And so, as we did last time, we're going to first assess the claim, and then we're going to use that to get our null and alternative, and then discard the claim from there. The claim is that the golfer can make par on at least 50% of the holes he plays. The fact that we're talking about a percentage of successes is what tells me this is a proportion problem and not a means problem. So that means my claim is that P is greater than or equal to 0.5. And then we said for directional claims, the alternative is that same direction, but we can never have or equal to. Then the null is the opposite of that, so that should lead you to the following hypotheses. As we discussed before, we can do our assumptions here, we can do our assumptions later, doesn't really matter. I copied and pasted the outline for these, so it's going to come in step 2, but again, if it came at the end of the problem, that shouldn't throw you for a loop. We could just work right into our test statistic and come back to that. It doesn't really matter. As we've said before, we always have to check number 1, is our sampling methodology sound? And notice that's what I'm writing here in the slides because I want you to come up with your own answer for this. All right, there's a lot of different things that you can put for this, and there's not necessarily just one correct answer. Okay, but we need to make sure that we have a representative sample. So this is a context-specific problem. You won't see any golf problems on the exam, so don't stress about that. But is this representative? Are all golf courses made the same? Are they all the same level of difficulty? What was happening weather-wise on this one day, right? So you could say a lot of things about whether you think this sample is representative or not. You could say here, if we treat this as a representative sample, then my results are good, right? So you have a lot of things you can say here. There's a lot of nuance, and it's just something to think about right here. Do we think that what happened on this one day in these 18 holes, do we think that is representative of what's going to happen for this golfer on all of the holes he plays, right? That's the whole point of this course is I don't know something about a parameter. I don't know about how much he makes par on all of the holes he plays. And so we watch this guy play one day, and what sort of inference can we make about him on the all holes based off of the sample? Well, if that sample is representative, we can make an inference. If it's not, maybe not so much. Okay. And then second, we need to check our mathematical assumptions. Check n times p naught, check n times q naught. Both of those equal 9, which is bigger than 5. And here I'm going to ask you another question because we also have to check if x is binomial, right? And my question to you, is x binomial? If it is, then all of our assumptions hold. Everything looks good, but is x binomial in this case? Let's go through our options, right? We're playing 18 holes, so we know we have a fixed number of trials. That there are 2 options, and you can't do them both at the same time either. He makes par, you don't even have to know what par is, it doesn't even matter, right? He either makes this thing or he doesn't. And then we have to check are the holes independent of each other. Is the probability that this golfer succeeds or not on the holes the same every time? Are they independent? Is that probability of success constant? Right? And I imagine most of you, if you haven't played golf, you've at least played putt-putt. And, putt-putt works a little bit different, sure, but you know that every hole isn't the exact same, right? If you just think about maybe as a kid playing putt-putt or even recently, it doesn't matter. Some of the holes are harder than others, right? And so your probability of success may not be constant. If you know anything about, full 18-hole, 72 par golf, you would know that there are holes of drastic different lengths, some with trees in them and some with water and some with more sand and some where the holes curve around the other direction, right? They're all drastically different. And so I would question if x is binomial because I would say I'm not really sure that the probability of success is going to be the same on each hole. Some holes are easier than others. Some holes are harder than others, right? And so this is a situation where if you were to see, and you won't see golf, you won't see anything sports in the exam, so you don't have to worry about that. But this is a situation where I'd want you to say, is X binomial and say, you know what, I'm not sure it is. I'm not sure this certain assumption holds. Those are the types of things that you want to be looking out for. You don't want to just write down on your assumptions, yeah, my sampling methodology is sound and yeah, everything looks good. Maybe it does, but maybe there's something there that I'm looking for you to catch. I want to see if you're thinking through the problem rather than just flying through it. So definitely some questionable assumptions on this problem. And then we're going to take our sample statistic, p hat, we're going to standardize it into the appropriate test statistic, just like we did before, value minus mean divided by standard deviation, plug in the right numbers. Now here, we aren't given p hat in the problem. Notice we are given a number of holes and a number of successes. We are not given the proportion of successes from the sample. This shouldn't throw us for a loop. It's one extra step that we have to do because we have to say the sample proportion is equal to the number of times we were successful divided by the number of trials that we had. We've been doing this type of proportion work for most of the entire course. And so we can say that if we had 13 pars out of 18 tries, that our sample proportions 13 divided by 18 are 0.722. Plug that in, and then we just plug and chug to get a test statistic of 1.88. We're going to, again, work the problem using the rejection region and the p-value method. This time we have a right-tailed test, so I'm only going to shade to the right. Again, not given a significance level for the second time in a row, so we're going to make sure that we use 0.05 for the significance level. We have to figure out what that cutoff value is. There's no cutoff value over here because it's just a right-tailed test. That cutoff value is 1.645. And so since this is 1.645, 1.88 falls in the shaded region, so we should be rejecting the null hypothesis. Let's see if we get a small enough p-value to validate that. Our p-value, now before we always had to figure out, if it was a two-tailed test, we had to say, we had to multiply by 2 and we had to use the sign of the test statistic to tell us the sign in the probability statement. But if we have a right-tailed test or a left-tailed test, we just go that direction and don't have to worry about it. So in this case, we have a right-tailed test, so we just have a greater than probability statement. Make sure here that you're not plugging in the critical value, right? When we find our p-value, we do the probability that the test statistic is greater than or equal than the test statistic that we got, right? So we're going to plug our test statistic into our p-value, not the critical value. If you plug the critical value in, you should just get alpha. Wouldn't do you very much good, right? This is a greater than probability statement, so we're going to want to work to a less than. That's how our z-table works. Work with a complement there, find the correct value, and we should land at a p-value, again, less than alpha, which would lead to rejection of the null, just like the rejection region method. So again, we have aligned on that answer. And as before, we're going to wrap it up with our justification of why we can reject the null. We say because our test statistic falls in the rejection region and our p-value is less than alpha, we reject H naught. And again, if the problem only asks you to work it one way or the other, just put that one piece, right? If it's just the rejection region method, don't talk about a p-value. If it asks you to use the p-value method, don't talk about if it falls in the rejection region, right? Just talk about whatever the problem asks you to. I'm doing both, right? But if a problem only wants you to work it one way, there's no need to talk about the other one, right? If you have extra time on the exam, you can go back and work it just to kind of confirm, that you're doing it right, but there's no need to work it both ways. This is just for practice. And then we're going to close off by saying because we've rejected the null, that means we can conclude the alternative. Just remember, and if you hadn't paused already and worked through it, see if you can give it a go right here. Make sure there are 5 pieces of information that you need when you write out the alternative. You need some population word, you need the metric, you need the context of the problem, you need the right symbol from the alternative and the number from the alternative. Make sure you can get all 5 pieces. So we're going to say at the 5% significance level, there is sufficient evidence to conclude that the actual, there's the population word, percentage, there's the metric of pars this golfer makes, there's the context of the problem, is more than, that's the symbol from the alternative hypothesis, that greater than symbol, 50%, that's the number from the alternative hypothesis. So we have all 5 pieces there. Again, we could have put that the actual proportion of pars this golfer makes is more than 0.5 or more than half. Right, is another way you could have said that would have been just as correct.